Well, let's do some section 14.2 numerical examples. The first example will be on page 387. It's problem number 2. And the reading of the problem: the density of a cold interstellar cloud prior to collapsing might be about 1.67 times 10 to the 20th kilometers per meter cubed. How many cubic meters of this cloud would contain enough mass to build the sun? That's part A. Part B, what is the ratio of this volume to the present volume of the sun? That's part B. And part C, what is the volume of cloud required if written in cubic light years? So part A, how many cubic meters of this cloud would contain enough mass to build the sun? We have to remember that what we mean by density is the mass of an object divided by its volume. So bricks have a greater density than wood, even though the pieces are of the same size, because it's thicker. So density is a sort of a measure of thickness. So we have density equals mass over volume. Now, if we multiply each side by V over D, then we see that the D's cancel out here, the V's cancel out here, and we arrive at the volume is equal to the mass divided by the density. Now, in this problem, we're given that the density of the interstellar cloud is 1.67 times 10 to the minus 20. And we know that the mass of the sun is equal to 2 times 10 to the 30 kilograms. And we get that from the data table near the back of the book. And we have 2 times 10 to the 30th divided by this. Now, since we're only doing a rough estimate, we will simply cancel out the 2 with the 1.267, and we arrive at the answer. If we use our rules of exponent, that a to the m, a to the n divided by a to the m is a to the n minus m, then we have that 10 to the 30 over 10 to the minus 20 is equal to 10 to the 30. Now there's a minus sign from the rule, and another minus sign from the minus 20, so it's equal to 10 to the 30 plus 20, or it is equal to 10 to the 50 meters cubed. So we have found that the volume of the interstellar cloud that would collapse into the present volume of the sun is 10 to the 50 cubic meters. In other words, this amount of volume of the interstellar cloud contains the same amount of mass that is now present in our sun. So let's go to question B. What is the ratio of this volume to the present volume of the sun? Well, this volume is 10 to the 50. We've just decided that. Cubic meters. And now let's find the present volume of the sun. And our sun has a radius, which again is found in the data table, of 6.96 times 10 to the 8th meters. And it is a sphere, so we know that the volume of a sphere is equal to 4/3 pi r cubed. So it's equal to 4 over 3 times 3.14 for pi times, and we're going to approximate that as a 7 times 7 times 10 to the 8th cubed. Now, since we're doing rough approximations, we'll just take the 3.14 and the 3 to cancel out. So we're left with 4 times 7 cubed times 10 to the 8th cubed. Now, 10 to the 8th cubed is an example of a to the n to the m, which is equal to a to the n dot m. So this is equal to 10 to the 24th. Now, 7 cubed is about 350. So this becomes 4 times 350 times 10 to the 24th. And 4 times 350 is about 4 times 250, which is 1,000. So this is about 10 cubed times 10 to the 24th. So this is about 10 to the 27th cubic meters. Now they want the ratio of the cloud that we have in question to the sun, and so the cloud that we had in question, so the ratio is going to be 10 to the 50 over 10 to the 27th, which is going to be that the cloud is 10 to the 23rd times bigger. So we found the ratio of the interstellar cloud, which ultimately collapses down to our sun. And they want to know what is the volume of the cloud required if written in light years. Okay. Well, 1 light year is approximately, so now we're doing part C, and 1 light year is the distance that light will travel in 1 year. Now, the speed of light is 3.0 times 10 to the 8th meters a second. And there are 3.2 times 10 to the 7th seconds in 1 year. So if you multiply these two together, then you are going to get the number of meters that are in a light year, and 10 to the 8th times 10 to the 7th is 10 to the 15th, and we get another 10 from those factors, so this is approximately equal to 10 to the 16th meters, is the distance of a light year. Now we want to know how much is a cubic light year. So a cube has a length times a width times a height, and each one of these would be 10/16. So the volume of a cube is length times width times height, so it equals 10 to the 16th cubed, so it is equal to 10 to the 48. Now our volume of the cloud from part A was equal to 10 to the 50. So if we have 10 to the 50 meters cubed, and each light year is 10 to the 48 meters cubed, then what we have are 200 cubic light years. And again, we're using one of the rules of power of 10, that a to the n over a to the m is equal to a to the n minus m. So 10 to the 50 over 10 to the 48 is equal to 10 squared, and 10 squared is 100. So let's straighten that out. It is equal to 100 cubic light years. So that will take care of that problem. And the next problem that we'll look at is number 3. So we're now on page 388, number 3. So let's do a reading of the problem. We get jets from a T-Tauri star. So what we have is a T-Tauri star, and it's got jets coming out of it. Are measured to have speeds of about 300 kilometers a second. So the speeds of the jet V is about 300 kilometers a second. And how long would it take the ejected material to travel 2 light years? So what we want to know is the time that it would take for the jet to go a certain distance if it's traveling at a certain speed. Now we know that time is equal to distance over speed, and you can verify this from your everyday experience. If you have to take a trip of 120 miles and you're driving at 30 miles an hour, then it's going to take you 4 hours. So in this problem, the distance is 2 light years. So 1 light year, as we saw in the previous problem, is 10 to the 16th meters. So this is 2 times 10 to the 16th meters, and the velocity in question is 300 kilometers. So it's 300 times 10 to the 3 meters. So now these are over each other. So if we change that denominator just a little bit, we get 2 times 10 to the 16th, and this can be written as 3 times 10 to the 5th. Instead of 300 times 10 cubed, it's 3 times 10 to the 5th. So we have 2/3 times 10 to the 16th over 10 to the 5th, which is equal to 0.67 times 10 to the 11th, using our usual rules of exponents. So this is now in seconds, so this is equal to 6.7 times 10 to the 10th, and this is in seconds again. So we know that if we want to get this in years, we have 6.7 times 10 to the 11th seconds, and this is over 3.2 times 10 to the 7th, which is the number of seconds in a year. And what we're going to come out with as our answer is about 2 times 10 to the 4th power. So we have to make a slight change up here. There's a little error. If we change this from 6 to 6.7, then we have to change this exponent up to a 12 to make up for the fact that, oh, this will go down to a 10 now. So that's going to change. And now this comes down to a 10. And we're going to get 2 times 10^3, which is going to be about 2,000 years.